Okay, they just informed me that the coffee is coming, so if you want to have some coffee to be awake for the next session, be here soon. And but I think now also it's time to start the session. And so let me introduce Costantino Arfanakis from Illinois Institute of Technology, and he's going to talk about group comparison and diffusion using diffusion imaging. Thank you.
Thank you, Flavio. Thank you for the invitation. Let's see if this clicker works. Hopefully I'm not going to put you to sleep, but I don't guarantee it. So we're going to be talking about group comparisons using diffusion imaging. Yes, it works. So a number of studies have used diffusion imaging to probe brain architecture and structural integrity in health and disease. And what we're going to be talking about today is an overview of approaches for group comparison of diffusion imaging data. We're going to list the advantages and disadvantages of each approach, and we're going to provide some tips for enhancing the accuracy of group comparisons. We're going to use DTI as our basis, and then we're going to briefly talk about how we can adapt all of these ideas for other diffusion imaging models. So here's the overview of my presentation. We're going to start with spatial normalization in DTI and the role of registration algorithms, templates, and what's the role of the quality of our data in the accuracy of spatial normalization. Then we're going to move on to traditional voxel-based group comparisons and what we can do better if we use voxel-wise analysis on the white matter skeleton. We're going to follow that up with ROI-based group comparisons, and finally we're going to discuss briefly how to do group comparisons for other diffusion imaging models. So let's start with spatial normalization in DTI. Spatial normalization actually plays a central role in group comparison of diffusion imaging data. And any study that uses spatial normalization, its accuracy depends on the accuracy of spatial normalization. And then the accuracy of spatial normalization depends on these three factors. Depends on the registration approach that you use, on the template that you use, and the quality of your data. So what we're going to do first is to discuss what is the effect of each one of these factors on the accuracy of spatial normalization. So there is a number of approaches that have been reported for achieving spatial matching of DTI data. Here we're going to list the most commonly used ones. So the first approach that was used early on is to register T1 or T2 weighted data across people, then to apply the resulting transformations to the FA or trace maps, and finally to perform tensor reorientation so that you can do comparisons of orientation-dependent quantities. However, this approach has some really important problems. The first one is that you have imperfect matching between the T1 or T2 weighted data and your DTI data. Which means that if you calculate your transformations based on T1 or T2 weighted data and you apply them to the FA data, you're going to be applying the wrong transformations in some parts of the image. Another problem is that registration is based on anatomical features. So your goal when you're normalizing T1 or T2 weighted images is to match the features in T1 or T2 weighted images. However, the features in FA maps are very different than the features in T1 or T2 weighted images. So what you're doing is not guaranteeing matching of DTI data. And finally, if you calculate rotations from T1 or T2 weighted images, you're not guaranteed to match tensor orientation across subjects. So this approach for registration of DTI data is not recommended. Another approach to perform registration of DTI data is to register maps of tensor-derived scalar quantities across people. So you can register, for example, FA maps across people. And then again, if you're interested in performing comparisons of orientation-dependent quantities, then you also need to perform tensor reorientation. The main problem with this approach is that, again, the rotations that you calculate based on registration of FA maps does not guarantee matching of tensor orientation. The third approach, which is recommended, is to actually register directly tensors across people. The main disadvantage here is that it's more time-consuming, but it's worth it because, as several studies have shown, tensor matching, tensor-based registration does the best matching of tensor properties across people. So, let me see if I can point. So over here, what we're looking at is we're looking at a comparison of tensor matching for different types of registration. So in the first case, we're using T2 information to do the registration. In the second case, we're using FA maps. In the third case, we're using differences of eigenvalues. In the fourth case, that AT stands for using both FA and trace information. For the second to last, we're using all the eigenvalues, and for the very last case, we're using full tensor information. So as you can see, using full tensor information gives you the best tensor matching. And of course, there's many other ways to do registration. For example, you can combine T2 and FA information, or you can combine T2 and full tensor information. You can do all kinds of things. However, tensor-based registration generally does pretty well in matching tensor information across subjects. So now, should we be doing a rigid body, affine, or nonlinear transformations when we're trying to normalize DTI data across subjects? Here you see a comparison of the mean of FA maps from multiple people that have been normalized using rigid body transformation and using nonlinear transformation. And as you can see, the nonlinear result seems to be a little sharper than what you get with rigid transformation, mainly in the periphery of the brain, and it also looks more realistic. It looks more like an individual FA map, so this suggests that the registration across subject has been more accurate. In this particular study, they looked at dispersion of tensor orientation for data sets that have been normalized using nonlinear registration in the bottom and the linear registration in the top row. And as you can see, when using nonlinear registration in the bottom, the dispersion of tensor orientation is lower than the dispersion of tensor orientation that you achieve with linear registration. So what is suggested is to use tensor-based nonlinear registration because it seems like it provides overall very good tensor matching across multiple subjects. There's a number of tools that allow you to do this, and here I'm showing you a simple example of what can be done with tensor-based nonlinear registration. S1 is one data set, the data set from one subject that we're trying to register to S2. And then we have three different registration algorithms that we used. We used SPM5 based on FA information, DTI-GUI that is based on FA and trace information, and then DTI-TK, which is based on the full tensor. And if you focus in the region within the rectangle, you see that SPM5 and DTI-GUI didn't do a very good job at replicating the feature seen in the S2 source image. However, if you look in the S1 DTI-TK top right corner, you see that within the rectangle we've done a good job at replicating the feature that we see in the S2 source image. So this is just a simple demonstration of what tensor-based nonlinear registration can do for you in terms of matching across subjects. The next factor that affects the accuracy of spatial normalization is brain templates. Diffusion imaging brain templates are used as references for spatial normalization. We have different types of diffusion brain templates. We have the standardized templates that are built once and are used in multiple studies. And we have the study-specific ones that, as the name says, they're built specifically for the study. And you can further divide these two categories according to their contents into templates that have full tensor information and templates that have only FA information. Or you can divide them according to their construction into templates that are constructed based on data from an individual subject, or templates that are constructed based on data from multiple subjects. So here is a listing of popular standardized DTI brain templates. And as you can see in the bottom row, they have different contents. So the Enigma template and the fMRI B58 template are FA-only templates. All other templates listed here are tensor-based. They have full tensor information. The Enigma template and the HCP488 that was recently introduced are based on at least 400 subjects. All others are based on less than 100 subjects, and actually Eve is the only one in this listing that is made out of a single subject. And then if you look at the bottom row, the Enigma, the ICBM 81, fMRI B58, and the SRI 24 are based on data collected from subjects with a wide age range, so from 18 to about 85 years of age. The IIT version 4, the Eve template, and the HCP 488 are built based on data from 20 to 40-year-olds. So if you do a quick scanning visual inspection of these templates, you will notice that there are two templates in this list that have the highest image sharpness. So that's the IIT version 4 and the Eve template. And if you think also that the Eve template is a single subject data set, and the fact that IIT version 4 has features that are very similar to those of Eve, it demonstrates that the IIT version 4 has features that are representative of individual subjects. If we compare these two templates now to the Enigma template, you will notice that it's relatively blurry throughout the image, especially in the periphery. For ICBM 81, we see the same thing. It's relatively blurry throughout, but especially in the periphery of the brain. For fMRI B58, it's a little sharper, but the problem here is that it's an FA-only template. For SRI 24, the issue is not mainly the sharpness, but the fact that the FA map looks non-typical. And for the HCP 488, again, we have significant blurring in the periphery of the brain. And also, there is a severe asymmetry between the left and right FA values. The right hemisphere FA values are substantially higher than the left. And also, some of the FA values in different parts of the brain here are higher than 1. So let's summarize the similarities and differences of the different standardized templates. The Eve appears to have high image sharpness and high SNR, but the main issue here is that it's a single subject data set, which means that you may get a bias. It may not be representative of the general population. The IIT version 4 has high image sharpness and high SNR similar to Eve, and it's a population-based template, which may be more representative of the general population. Also, the features that it has are very similar to the features seen in the single subject Eve template, which means that it's representative of the data of individual subjects. And it's also located in ICBM 152 space, which is convenient because it's a very popular space. Now, if we compare the other multi-subject templates to the IIT version 4, the ICBM 81 template is blurrier than IIT version 4. Demonstration is shown here. On the right column, you see results from IIT version 4, and on the left, you see results from ICBM 81. You can see that the anterior commissure and the decussation of the superior cerebellar peduncle, DSCP, are clearly seen in the IIT version 4, but they're not visible in ICBM 81. Also, the ICBM 81 has lower FA values compared to IIT version 4, and one of the reasons is misregistration of the individual subjects. The way this happens is that if you have multiple tensors that are nicely registered to each other, then their mean is a tensor that looks like them. But if you have misregistration and you average those tensors, the mean becomes a more rounded ellipsoid, and the FA value drops. So that's one of the reasons why ICBM 81 has lower FA values. The other reason is that it is made out of subjects with a very wide age range, and as you know, FA value drops with age. Now, if we compare the Enigma and fMRI B58 to IIT version 4, they're both blurrier and both have lower FA. And also, one severe problem with those is that they do not allow tensor-based registration, which, as I showed you earlier, gives you the best spatial matching across subjects. In terms of SRI 24, that template is blurrier than IIT version 4. It has lower FA, and it also has an atypical FA map. In terms of the recently introduced HCP 488, it's blurrier. It has an atypical FA map with a big asymmetry between left and right hemispheres, and also several regions have FA values higher than 1. So according to all of these similarities and differences, advantages and disadvantages, it seems like in terms of multi-subject atlases that IIT version 4 has several of the desirable characteristics for templates. So let's keep that in our mind. We're going to come back to this very soon. In terms of the study-specific templates, the way to construct them is to use the data collected for a certain study, and we're going to use that same data set in order to make the study-specific templates. There are 3 different approaches for making study-specific templates, and we're going to discuss each one of them separately. So the first approach is to normalize all subjects, so I1, I2, I3, IN. We're going to normalize all subjects to one of the subjects that may be the most representative one. So let's say this one is I1. So we're going to perform all of these registrations. We're going to generate these new data sets I11, I21, I31, IN1 that are in the space of I1. And then we're going to combine them to make a template. To do this, we only need n-1 registrations. The reason why we don't need n is because we don't need to register I1 to I1 again. This is not a recommended approach, although fast, because the final template that we're going to get is in the space of I1 and it looks like I1, so it looks like an individual data set which may not be representative of the population. So let's move on to the next approach. The next approach is to normalize all subjects to all other subjects. So I1 is registered to all subjects. We generate these n transformations. We combine these n transformations into 1, and we apply them to I1, and in this way we generate I1 prime. This I1 prime is sitting in population space. We then do the same thing for I2. We register it to all others. We generate these n transforms. We combine these n transforms into 1. We apply it to I2, and this is our I2 dataset in population space. And we keep doing this, and in the end, we combine all of these new data sets to make our template. Now, this is a great template. The only problem is that it's very time consuming. In order to get to this template, you need to do n times n minus 1 over 2 registrations. The reason why you don't need n times n registrations is because in this looks like a matrix, the T11, T22, T33, T and n, you don't really need to estimate because it's registration of the subjects to themselves, so you don't need to calculate anything there. And also whatever is below the diagonal is the inverse of whatever is above the diagonal. So the only transformations you need to calculate are really on the top side of the matrix or the bottom of this matrix. So it's still maybe not n times n registrations, but n times n minus 1 divided by 2 is a large number of registrations, so it takes a long time. This is a great template, but it's very time consuming, and for that reason, it's not recommended. But if you have time, you can definitely do this. The recommended approach is to do the following, to register all of your data sets into a temporary template first. This temporary template could be a standardized template, or it could be the mean of your data sets after rigid body registration. There are different options there. So you register all of them to this temporary template, you generate new data sets, you combine those, you get a new temporary template, you use that second time, you register everybody to that template, you combine those, you get a new temporary template, you use that for registration, you get another temporary template. And you keep doing this for several iterations. And in the end, after several iterations, you just pick the last template as the template to use. So this generates a decent, a very good template. And you only need n times the number of iterations registrations. So it's faster than the previous approach, and it generates quite good template. So for that reason, it's recommended. So what we're doing next is, now that we have a good background on registration algorithms or registration approaches and templates, the goal in this comparison was to see how different registration approaches affect spatial normalization accuracy. So what we're doing here is we're comparing 3 different registration techniques, and keep in mind that it's only 3 registration techniques. It's not 50 or 20 or whatever, so we do need more studies on this case. So we're comparing DTI GUI that uses FA and trace information, Medinria and DTI TK that are using tensor-based registration, and we're using study-specific templates. And what we see is that the DTI TK generates better, higher spatial normalization accuracy. Now, we also compared standardized and study-specific templates in terms of spatial normalization accuracy. And we saw that when we were using DTI data with typical susceptibility artifacts, typical EPI artifacts, we saw that study-specific templates, shown here in the solid black line, gave higher spatial normalization accuracy compared to what we got with the IIT version 2 template and ICBM 81. However, when we used the artifact-free DTI data, we saw that the study-specific template and the IIT version 2 template gave nearly identical spatial normalization accuracy. So the conclusion from this is that as DTI data quality improves, a high-quality standardized template results in similar normalization accuracy as a study-specific template. So if you dig a little deeper, essentially, when you have artifacts in your images, a study-specific template better captures this behavior than any standardized template. But when these artifacts go away, then if you have a template, a study-specific template that was made out of 100 brains, and a standardized template that was made out of 100 brains, they're both relatively representative of the data under study in that case. So it's mainly the distortions, artifacts, and other characteristics that make the study-specific template more representative of the data under study. So as DTI data quality improves, I believe that high-quality standardized templates provide similar normalization accuracy as study-specific templates. So here we're comparing different standardized DTI brain templates in terms of normalization accuracy. In this particular case, we use the EPI data, and what we see is that IIT version 4 gave the highest normalization accuracy, followed by ICBM 81, which was followed by the EVE template, which was followed by fMRI B58, and the last one was SRI 24. Again, this is a comparison among these 5 standardized brain templates. So what are the advantages and disadvantages in general of standardized and study-specific brain templates? Let's start from study-specific templates. The main advantage is that it's most representative of the data under study. However, this is theoretically the most representative of the data under study, because if it's not well constructed, then that study-specific template actually performs worse than any standardized template. So it needs to be very carefully constructed. If you have a small number of subjects, for example, or if you use inaccurate spatial normalization, the title study-specific template doesn't make it the best to use. Okay, so that's a very critical point. It also takes time to construct study-specific templates. You typically don't have any gray matter labels or white matter labels or other features of an atlas associated with that. The differences in study-specific templates across studies also complicate the integration of results across studies. So these are the advantages and disadvantages for study-specific templates. In terms of standardized templates, if you use a high-quality standardized template, then you end up with consistently high accuracy. You don't have to make a new template every time, so you minimize complexity. Since it's the same template used across studies, it facilitates integration of findings across studies. And if these templates are part of an atlas, you may have labels and other resources that are available to you. The main disadvantage of standardized templates is that in the presence of artifacts, it may not be the most representative, they may not be the most representative of the data under study. But as the DTI data quality improves with your connectome scanners and so on, this problem is corrected, and actually standardized templates and study-specific templates in terms of spatial normalization perform very, very similarly. So the summary about the spatial normalization portion of my presentation is here. So spatial normalization accuracy depends on the registration approach you use, on the template you use, and also on your data quality. In terms of the registration algorithm, tensor-based nonlinear registration performs quite well. In terms of tensor matching, DTI-TK is a package that allows you to do this. It's widely available, freely available, good support, and it's easy to use. In terms of the templates, again, study-specific templates are theoretically most representative of your data. However, you need to exercise caution here because, again, if study-specific templates are not very carefully constructed, they don't perform as well. They're not as representative of your individual data. So if your subjects are not well co-registered, for example, it will look blurry, and blurry is not representative of your individual data sets. So it's very important to do this very well. If you don't want to get into this trouble, then you can use standardized templates, and IIT version 4 was shown to accumulate the most desirable characteristics. It also has a number of other resources that simplify your life. It has a number of anatomical templates, tissue probability maps, other DTI templates, a Hardy template, a probabilistic gray matter atlas based on the Desic and Kiliani labels, and another one based on the Destriot labels. And recently we added a probabilistic 4D connectivity-based white matter atlas. It's 4D because we realized that every single voxel probably contains more than one connections. Therefore, each voxel in white matter of this atlas contains multiple labels that correspond to different connections. It's connectivity-based because we are mapping connections between regions of our Desican version of our gray matter atlas. And it's also dynamic because by doing different combinations of the gray matter labels, for example, if you group all the temporal lobe gray matter labels together and all the frontal lobe gray matter labels together, you can generate a new map, a new atlas, like the one shown in the bottom. So standardized templates, if they're part of an atlas, they may have other perks. Finally, going back to spatial normalization accuracy, you need to keep in mind that data quality is very important. You cannot expect low-quality data to normalize very well, even if you use DTI-TK, tensor-based nonlinear registration, good templates, and so on. So data quality is of very high importance for spatial normalization accuracy. So now let's move on to traditional voxel-based group comparisons. There are 3 steps here. The first step is to perform spatial normalization across data sets. The second step to do smoothing. And the third step to perform your statistical analysis voxel-wise. But traditional voxel-based group comparisons have some important limitations. First, the combination of misregistration with the fact that FA maps have very high contrast gives you a number of false positives along the edges of white matter. In the left 2 pictures, you see false positives near the splenium of the corpus callosum, shown in light blue. This was generated because you had a lot of misregistration, because you used linear registration. Now, if you use nonlinear registration, you see that the problem is reduced, but it's not completely eliminated. So there's a number of studies early on that used traditional voxel-based group comparisons that had this problem. You can see what happens in the corpus callosum, in the front and the back of the brain. You see significant effects all along the edges of the white matter. The same thing over here. You see it in the internal capsule. You see it in the corpus callosum, and so on. So that's one big problem of traditional voxel-based group comparisons. The second problem is that we don't really know how much to smooth our data sets. So the second step, as we said, is smoothing, and we don't really know how much to smooth. In this particular study, Jones et al. Compared the result after 4 different levels of smoothing. So they used a kernel with 8 millimeters full width half max, then another one with 10 millimeters, another one with 12 millimeters, another one with 14 millimeters. And if you look at this particular region over here, it looks very strong at 14 millimeters. It becomes smaller for 12 millimeters, then becomes even smaller, and then disappears. And then if you look at this region over here, it becomes stronger from 8 to 10, even stronger at 12, and then goes away at 14 millimeters smoothing. So for one region, 14 millimeter smoothing is the best. For the other region, 10 millimeter smoothing is the best. So which one should we use? Nobody really knows. So these are the 2 big problems of traditional voxel-based group comparisons. They're very sensitive to misregistration, and we don't know how much to smooth. And for these 2 reasons, traditional voxel-based group comparisons are generally avoided. In the next section of my presentation, we're going to be talking about voxel-based group comparison along the white matter skeleton. This approach was developed to address the problems of traditional voxel-based analysis of DTI data. And I'm sure you all know about TBSS. This is the approach that I'm talking about. Tract-based spatial statistics, that's what it stands for. It has the following 4 steps. In the first step, we have special normalization to a target. Here you see on the left in red the outline of the target, and in grayscale you see the individual subjects. After a fine registration to the target, you see that the registration has not allowed perfect matching. But after a fine and nonlinear registration, you see you have a better matching. But still it's not perfect, and that's what we're trying to solve through TBSS. In the following step, we skeletonize the white matter of the target. We basically thin out the FA map, and we generate this white matter skeleton shown in green. And in the third step, which is the centerpiece of TBSS, we're projecting information onto the skeleton. Okay, so the yellow line corresponds to the skeleton, the white matter skeleton. And then the grayscale information is the tract that should be matched with that yellow line, with that skeleton, but it's not for 9 subjects. So in this step, in the projection onto the skeleton, we're projecting information from the center of the tract, and we pick the center of the tract using the highest FA values that we can find. So we're grabbing the highest FA values and we're projecting them onto the skeleton. So the idea here is that even if you don't have perfect spatial matching across subjects, by searching around the skeleton, perpendicular to the skeleton, and grabbing these intensities from the highest FA regions, you're going to be essentially eliminating the problem of misregistration. You're not going to be eliminating, we'll talk about it, but that was the intended, that was the reason for this step. And then in the end, after you have all your data on the skeleton, you perform statistics like you would in a voxel-wise analysis. You can use a general linear model. Because your data after the skeletonization part are Gaussian distributed, you can use simple parametric tests. Or if you want to avoid those, you can use your permutation-based approaches. You can do your family-wise error correction. You can use your threshold-free cluster enhancement to do the analysis. So the advantages of TBSS are that it's less sensitive to misregistration, not immune, less sensitive to misregistration. No smoothing is necessary, so there goes the smoothing. And then you have a smaller multiple comparisons problem because you have fewer voxels that you're comparing, so fewer statistical tests. But TBSS also comes with limitations that are important, and you should be aware of those as you're processing your data with it. The first is that the default spatial normalization steps in TBSS are not ideal. So in this study by Kehaninejad in 2012, they compared the standard deviation of FA maps after normalization to the fMRI B58 template to the most representative subject, and to the average of your data after registration to fMRI B58. So the first 3 rows are the options that you have through TBSS for normalization step. So what Kehaninejad did, they showed that standard deviation is actually lower if you register to a good study-specific template. I should point out here that even that study-specific template is not perfect because it was constructed using FA-based registration, not tensor-based registration. So you can basically do much better than what the bottom row shows there. So why do we care about misregistration, residual misregistration? Isn't TBSS going to fix that? Isn't that the reason why we're doing the projection? That's the reason why we're doing the projection, but TBSS is not going to try to find the correct values to project into the skeleton all over the place. So if you have misregistration, it's still going to affect your data. A recent study demonstrated that the projection to the skeleton actually addresses about 10% of the misalignment. So you still need to do very good spatial normalization in TBSS, and if you use the default options for normalization, you're going to get many false positives as shown in the top 3 rows compared to the bottom row that has far fewer false positives than the top 3 rows. And as I said, even the bottom row is not the best spatial normalization you could have done. So the first recommendation regarding TBSS is that you should replace the default option with optimal normalization strategies. And what are these optimal normalization strategies? Well, it's tensor-based nonlinear registration using a high-quality either study-specific template or a standardized template. And you can do that on your own. You don't have to use the tools that you have through TBSS. Now, another limitation is that only voxels at the center of tracts are studied. So if you're looking for some abnormality that is happening outside of the center of a tract, you're not going to find any significant differences. You're not going to see a significant effect. The other problem is that a lesion that may happen at the center of a tract may affect the values at the center of the tract, and that may force TBSS to project onto the skeleton values that are not sitting at the center of the tract. So in the end, you're going to be comparing center of tracts with some other tissue sitting somewhere else. Another interesting limitation is the fact that TBSS has higher sensitivity in diagonally oriented tracts compared to horizontal tracts or vertical ones. So diagonally oriented tracts are, for example, the tracts in the internal capsule, and you see how the internal capsule is thicker than the external capsule and optic radiations. So when you use also your TFCE, threshold-free cluster enhancement, that enhances effects that are shown over a larger number of voxels, you tend to bring up effects that happen in these thicker bundles than the thinner bundles. As Eden and Jones showed very nicely, when this happens, you get more power in the internal capsule and less power in optic radiations, simply because of the thickness of the skeleton. Similarly, if you have 2 studies that are using 2 different skeletons from study-specific templates, for example, you get different power for the same part of the brain. Here, the skeleton on the right has less power in the optic radiations than the skeleton on the left. Similarly, for the internal capsule, you have more power for the skeleton on the right, less power for the skeleton on the left. So your power depends on the orientation of your skeleton. So the recommendations about the projection to the skeleton step are first to realize which portions of the brain are actually included in the analysis. You're not comparing all of the brain, you're comparing only what happens in the centers of tracts. Second recommendation is that you should avoid single subject skeletons because they're very noisy, and you should prefer skeletons that are derived from either high-quality study-specific templates or standardized templates. Another important issue I should mention here is that standardized templates can actually provide important benefits in TBSS. Standardized templates can give you a good template for the special normalization step. They can give you a nice skeleton, and they can also provide standard sensitivity across studies, because the positioning, the orientation of the skeleton is always the same from study to study. So you don't have the rotation that changes the power, basically. Another thing, if you have a standardized template which is associated with an atlas, again, you have more available resources. So let's say you do TBSS and you find some part of the brain that shows a significant difference, in this case, a region in the corpus callosum, and you say, I don't know which fiber bundles are in those regions. What can I do? Well, if you've done the analysis in IIT space using the IIT skeleton, then you can actually extract that ROI and perform Hardy tractography on the IIT Hardy template, which will give you the parts of the brain that have connections through that ROI. So this means you don't have to have Hardy data in order to do this. You can actually use the Hardy data within the atlas in order to do this connectivity. Now, what if you say, I can't read the skeleton and I don't want to run Hardy tractography because it's time consuming, but my data are in IIT space? Again, if you extract this ROI and you run a script that is provided with the atlas that runs on that ROI and looks through the 4D white matter atlas, then in a few seconds or less than a minute, you're going to get a text file. The first column of that text file shows IDs for different gray matter regions. The second column shows IDs again for gray matter regions, and the third column shows confidence for the connection between the gray matter region in the first column and the gray matter region in the second column. So, for example, for this first row, we see that the connection between the left superior frontal gyrus and the right superior frontal gyrus is the most probable connection through that ROI. So basically, by using this atlas, you can answer the question that you always have after you get a TBSS result. What am I looking at? What kinds of fiber populations are included in that region that showed significance? So in summary, TBSS has advantages over traditional voxel-based analysis, but it also has limitations. Accurate spatial normalization remains crucial. We did not solve this problem. We reduced this problem, but we did not completely solve this problem. So it's important to get good spatial normalization accuracy. It's also a good thing to get a good skeleton. Skeleton characteristics are very important. And standardized atlases may help you in several parts of the TBSS process. But the most important take-home message about this part of my presentation is that you should be inspecting every single step of the TBSS process so that you understand in the end what kind of results you're getting and what things you're comparing in your analysis, and to make necessary enhancements when necessary. I've included some papers that discuss all of these issues that I'm presenting here today. Also, I should point out that there are alternatives to TBSS that are coming out, but currently it's the simplest to use tool. It's very widely used, and that's why we're talking about it so much. In terms of 5 minutes, okay. In terms of ROI-based group comparisons, we have the following 3 steps. We have selection of the ROI, extraction of information from the ROI, and then statistical analysis. And how you conduct ROI-based group comparisons depends on what the ROI is. So if the ROI is a lesion, or if the ROI is a fiber bundle that is defined with tractography, or if the ROI is a brain structure or fiber bundle that is segmented using atlas-based segmentation, or if it's part of the white matter skeleton that is defined with skeletonized atlas-based segmentation, depending on what the ROI is, you perform ROI-based group comparisons differently. So if you're interested in the diffusion characteristics of lesions, in this particular case, we're interested in comparing lymphomas versus glioblastomas. You select your ROI, you extract information, and you can compare either summaries of diffusion characteristics, histograms, etc. So you can make different graphs here that separate the characteristics of lymphomas and glioblastomas. If you're interested in group comparisons of fiber bundles, Dr. Garifalidis is going to talk about this next. You select your ROIs, you do your fiber tracking, and then again you can compare either summaries from the whole bundle or you can compare diffusion characteristics along the bundle. Now, in terms of atlas-based segmentation, if you want to extract certain structure from the brain using atlas-based segmentation, you first register the atlas to the individual subject, you transfer the labels to the subject space, and then you can use either anatomy-based labels, like from the EVE atlas, or probabilistic connectivity-based labels, like the ones shown here. But the main problem with atlas-based segmentation is that it's sensitive to misregistration. Again, here you need to perform optimal normalization, as good normalization as possible, but we know that you can never achieve perfect normalization. So an alternative to this is a skeletonized atlas-based segmentation. So the idea here is that you first specially normalize to atlas space. You perform skeletonization like in TBSS. You mask the atlas with the atlas labels with a skeleton, as done here. And then you project the information onto the skeleton, you extract summary measures, and you do your statistical analysis per skeleton segment. We've shown that the partial volume effects are substantially reduced if you use skeletonized compared to traditional atlas-based segmentation. The FA of the regions that are segmented are always higher than in the skeletonized versus traditional atlas-based segmentation. The trace values are always lower in skeletonized compared to traditional atlas-based segmentation, especially around the ventricles. And also the sample size is substantially improved when you use skeletonized over traditional segmentation. So I'll move on in the interest of time. The last thing I want to talk about is, let me skip this summary here. Everything's very fresh. The main issue I want to bring up is the final point here, that ROI-based group comparisons have a smaller multiple comparisons problem compared to voxel-wise analysis, so that's the main advantage of ROI-based group comparisons. Now, if you move on to other diffusion imaging models, in terms of group comparisons, the concepts are the same, the methods differ. So you may do FOD registration instead of tensor-based registration. Representative templates do exist. Again, you need to care about your data quality. The features that you're going to be comparing depend on the diffusion imaging model that you use, but you can still use similar analysis, voxel-based or ROI-based analysis. So the take-home messages, and this is my last slide, are first that spatial normalization is important in different types of group comparisons of diffusion imaging data. The registration approach you use, the template you use, and the data quality play a huge factor, have a huge role in spatial normalization accuracy. Traditional voxel-based analysis have important limitations. Some of them are alleviated with the use of TBSS. However, you need to be careful when you use TBSS, and you need to appropriately adjust different steps in TBSS. ROI-based analysis can be used to study lesions, brain structures, or even fiber bundles using appropriate atlases that have connectivity-based labels. And again, atlas-based segmentation suffers from misregistration, and skeletonized atlas-based segmentation can help reduce some of these problems. And finally, if you use other diffusion imaging models, the concepts are the same, but the methods differ. With that, I'd like to thank you for your attention, and Flavio and the organizers for their invitation.
Konstantinos. Do we have time for a quick question? I think, actually, we have time, sorry. Do you have a question now, briefly, before, because we are a bit behind schedule. Okay, one question.
So I think this is a misconception from conventional voxel-based analysis in VBM, for example, for T1 maps. So the problem here is that if the atlas, even let's say an FA map, if we're trying to do registration between FA maps, if the FA map of the template becomes blurry, then the registration step of an individual non-blurry FA map to that blurry target is not very accurate. So if you're trying to match this thin segment into this thick segment, it may end up anywhere. So to think about it very simply. So if you try then to match multiple subjects, by default they're not going to match very well because they could end up anywhere. So you want your template to be as representative of your individual subjects as possible. The problem DTI compared to VBM is that when you use T1 maps, they have very low contrast, let's say. So it's bright versus a little brighter. An FA map is dark versus very bright. So there the accuracy of spatial normalization is very, very important. And that's why you need an atlas and a template that is as sharp and as representative of your individual subject as possible. Of course, if you do registration, it's never going to be perfect, especially in the periphery of the brain, because there are differences across people. But you want to try to make your target as close to the individual subjects as possible.
Okay, thank you very much.